All right, problem of the day 23 is a refresh of chapter 4 chemistry with cycloalkanes. So the first compound I wanted you to look at was cis 1-bromo 4-tert-butyl cyclohexane. So let's draw this as a 2D structure. If it's cis, should the substituents be on the same side or opposite? Same. Okay, so I'll put the bromo up here as a wedge, and and the tert-butyl down here as a wedge too. And let's draw this in the chair conformation. So in this one, we've got our bromine sticking up. In this one, we've got our tert-butyl group sticking up. This is in equilibrium with its chair-flipped version. So let's draw our chair flip. All right, so if we do this, now our bromine's over here, and our tert-butyl is over here. Which one's going to be our major contributor, right or the left? Not everybody all at once. Left. All right. There we go. Why is the one on the left our major component in solution? Yeah, the tert-butyl group is very large. It does not want to be in the axial position. If it's axial, then you run into 1,3 diaxial interactions. So in this solution, what we could think about is we could say it's going to be 99% this side, less than 1% on the right side. So it is an unequal equilibrium. It's not a perfect 50-50 mixture. All right, so now what we have to do is we have to analyze our substrate in terms of the alpha and beta positions. So alpha position is right here. We've got some beta positions, and particularly we've got protons coming off of these beta positions. Oops. All right, so we've got these beta positions. Are either of these beta positions anticoplanar? What do you guys think? Yeah, so let's look at this with my chair that I made. Oh. See if I can get this together here. All right, here's the chair conformation. You see how the bromine's pointing straight up and down? That means the beta proton also has to be pointing straight up and down in an axial position. So in this case, it would be the lower hydrogens that are in the axial position that would be beta. So let's circle those. And we'll say these are anti-coplanar beta protons. An E2 reaction will not occur unless you have an anticoplanar beta proton. Let's do the same thing for our next reagent. This time we've got the trans-isomer. So we've got Br, and the tert-butyl is now a wedge. Let's draw this as a chair structure. So the bromine's still pointing up here. Tert-butyl group would be pointing down. We've got an equilibrium with our other chair. Let me clean this up a bit. There we go. Now this bromine's equatorial, and this tert-butyl group is equatorial. All right, which one's going to be present in solution at the greater quantity? The one on the left or the right? The right. Again, because the tert-butyl group wants to be equatorial, it's really unhappy when it's axial, so we'll say 99% less than 1%. Okay, so if we look at this, we can say, okay, there's our alpha position. We've got beta protons here and here. Then another set of beta protons here and here. Are either of those sets of protons anticoplanar? No. So let's look at this. If we look at our chair structure now, these protons aren't pointing in the opposite direction of the bromine. The other thing you could do to help is to actually do the Newman projection. So look down the individual bonds from your alpha to your beta carbon, and you see how the bromine is in between those two beta protons? that means that they're not anticoplanar. In fact, the carbon-carbon bond on the opposite side is anticoplanar. Same thing if we go through this alpha-beta Newman projection. If we go through that, again, our bromine is in between two of our beta protons. We don't have a beta proton that's anticoplanar. So if we look at this, we can label it and we can say there are no anticoplanar beta protons. All right, the challenge question that I was going to throw on here but didn't because I wanted to be kind was why can this even do an E2 reaction for the trans 1-bromo 4-terbutyl cyclohexane? What do you guys think? I said it occurs slower.
The 1% does have.
Yeah, so that's one half of it is we could take this, do a chair flip where they're both axial, and when the bromine's axial, it does have anticoplanar beta protons. But there's actually another story. If you look at a chair, it can also go through a conformation that's called a boat. And in this boat conformation, the terbutyl group is equatorial still, it's pointed out. And now the bromine's in what's called a flagpole position, and it's anticoplanar to beta protons. So this is one of the unique examples where the boat conformation does matter for a cyclohexane. We just aren't going to spend too much time on boat conformations because most of the reactions we will see rely on the chair conformation. The key thing to remember with this is that in cyclohexanes, your leaving group must be axial for an E2 reaction to occur. In the Klein textbook, he briefly touches upon this and he says that it needs to be axial, but he doesn't really go into much detail about why. The root reason is that you have to have a beta proton that's anticoplanar.
So what caused the compound to change its formation?
Do a chair flip?
Yeah, so what's the reason?
So it's just a matter of it being in equilibrium. So in an equilibrium, you do have things interconverting back and forth all the time. It's not that they're going to be in a perfect 50-50 ratio. It's that you might be 90-10, or you might be 99-1, you may be 75-25, but things are interconverting back and forth. So just like with an acid-base equilibrium, you've got a little bit on each side of the equation.
Well, I just want to know what might cause the formation, like pores, bonds, something.
So the question is, what might drive the conformation? The conformation that's favored will be the conformation where your largest group is equatorial. It does not want to be axial. That's what drives the major contributor in equilibrium. Okay, so let's continue on talking about E2 reactions. But I guess before we go on, are there any questions with the POD? No? A lot of blank stares at me. If you guys do get stuck on this, I really recommend breaking out your model kit. It's tough to see things in 2 dimensions on a piece of paper, but if you hold it in your hand, sometimes it's easier to rotate it and manipulate it around and then look for that anticoplanar beta proton. And remember that you guys are allowed to use model kits during your exams and quizzes, so if that helps you, make sure that you are prepared for that. Okay, let's go to chapter 8 again. So we finished off yesterday talking about E2 reactions, and we said E2 reactions are concerted second-order reactions where the rate is dependent on the concentration of your substrate and your base, and your beta proton must be anticoplanar to your leaving group. And then I said a nice trick is to draw your Newman projection and try to rotate it so that you do have an anticoplanar beta proton. And our challenge problem that we left with yesterday was the one drawn on the left, where in the conformation shown, we don't have an anticoplanar beta proton. In fact, if we look at this, the ethyl group is anticoplanar to our leaving group, so that doesn't work. And we said, in order to correct for this, we have to actually rotate this molecule so that that proton on the front carbon is now anticoplanar. So this proton up here, we need to rotate it into an anticoplanar position. And then as we were leaving, I said that the methyl group and the hydrogen are going to end up being cis to each other, and the ethyl group and the methyl group will also be cis to each other. So let's finish this reaction, and I'm going to redraw this as a two-dimensional structure. So we didn't change the front carbon, or we changed the front carbon, we didn't change the back carbon. So if we rotate it, we've now got a methyl group sticking straight up. We've got, let's see, a hydrogen going back. And we've got an ethyl group here. So now let's do this with our base. The base is going to go after our anticoplanar proton, which is right here. It's in our beta position. Then we need to clamp down, eject off our bromine. And when we look at our final product, we said that our methyl group on the back carbon is going to be cis to the ethyl group. So we'll put methyl group here for our back carbon. It's going to be cis to our ethyl group. And then for our back carbon, our hydrogen is going to be cis to our methyl group. Right? So if we look at this, is our product going to be considered cis or trans? Trans. If we look at the methyl groups, we've got identical methyl groups on opposite sides. So we'll get our trans product. We will not observe any of our cis product because there is no possible conformation that allows for the cis product to occur. So we'll say cis product not observed. All right, so this is a pretty unique E2 reaction. We only get one product out. We don't get any other products. And when we are referring to reactions where you only get one product, we call it stereospecific. So this E2 reaction is stereospecific. And stereospecific is just a unique way of saying that there is only one possible reaction pathway. You don't get a mixture of products. Mix of products. There are some E2 reactions where we do see a mixture of products, though. So we need to go back and we need to look at some situations where we might get a mixture of products and then analyze which one's going to be major and which one's going to be minor. So let's go back to a slightly easier example. All right. So let's do example number 2. In this one, I'm going to put a bromine as a wedge. Oop. Got a hydrogen here, and then I'm going to label these two hydrogens different colors. So I'll label this one H, and I'll label the back one H in blue. So let's draw the Newman projections for this. So let's again imagine we're looking down the beta position, going to the alpha position. What should be sticking straight up and down? The methyl group. All right? So I'll put a CH3 here. And then what's going to be going down to the right? The blue hydrogen. And that means our green hydrogen must be going to the left. And then if we look in the back, where's our bromine? Is it to the top right, top right, bottom left, or top right, top left, or bottom?
Top left.
Top left. There we go. I'm getting my tongue tied. Our hydrogen would be here, and then we've got our CH3 here. So if we look at this, we could say, all right, this blue proton is anti-coplanar to our bromine. But what if we rotate it? Let's try rotating this. And I'm going to only rotate the front carbon. I'm going to leave the back carbon static. So in this case, I'm going to rotate it so that our green hydrogen is over here. Where should our blue hydrogen go? On top. And our methyl group is going to be to the bottom left. Our back carbon, we said, stays exactly the same. We've got a hydrogen here. And we've got a methyl group here. And again, we have anti-coplanar protons to our leaving group. The question is, which one's going to be the preferred conformation? The first one or second? First one. Why is that? Yeah, the methyl groups are on opposite sides. If we remember back to chapter 4, I said this interaction right here is really destabilizing. What is this interaction called? Gauche. So we want to avoid Gauche interactions, but that doesn't mean that we don't see a mixture of products. We do have two different beta protons. So let's look at this. We said that this one's going to be our minor. This one's going to be our major. So let's redraw our starting material. And we're going to do a minor reaction first. Or sorry, let's do major first. So if we're going after our major product, are we going to go after the blue proton or green one? Blue. Okay. So in this reaction, we'll say, base is going to go after our blue one, kick down electrons, and give us this product. And if we think about what this product should look like, the methyl group should be cis to that hydrogen. This methyl group should be cis to that hydrogen. So let's draw our product out. Oops. We've got carbon-carbon bond with 4 substituents coming off. Our back one, we've got a hydrogen and we've got a methyl group. And in our front one, we said that our methyl group should be cis to this hydrogen. And wait a second. Sorry, hold on. My brain's getting shot here. This should be a CH3 up here, and this one should be green. I flip-flopped them. There we go. So we've got these groups cis to one another, just like we predicted, and we've got these groups cis to one another, just like we predicted, right? So the black CH3 and the black hydrogen are cis, and the black CH3 and the green hydrogen are cis. Yep.
So the black one is just the one where the bromine is?
Yeah, imagine, so let's try this. Imagine our eyeball for a Newman projection was originally looking down there. Now we're looking down here, right? So if we look at that front carbon, we've got a hydrogen that's green left, and then a methyl group that's left, right? And then in the back carbon, the one behind it, we've got a black hydrogen that's left, and we've got a CH3 that's left. So we're just trying to pair those up. Yep.
Can you draw a Newman projection down a double bond?
Yeah.
Do you do it differently?
Typically, people don't draw very many Newman projections down a double bond because everything's eclipsed. They're forced to be eclipsed, so it doesn't really give you that much information. Yeah, so if we look at this, we could say, all right, this is going to be our major product. And is our major product going to be cis or trans? Trans. All right, now let's do the same thing, but with our minor product. So this time we're going to redraw our starting material. We've got our bromine in the back, our hydrogen here. But this time, we said that our green hydrogen is going to be going back and our methyl group is going to be going forward. So we want our green hydrogen here, our blue hydrogen over here. All right. Now we've got our base. Our base, we said this time, is going to go after our green proton, not our blue one. And we're going to kick off our bromine. We've got a CH3 here, CH3 here, and our blue proton is left over. All right, and we said that this one is going to be our minor product. And it is going to be cis. So in these reactions, we don't get one product, we always get a mixture of products, but we're going to usually favor the one that's the result of the less destabilized Newman projection, or the one that results in the trans product, typically. In this case, we're not exclusively getting one product, so we have to refer to this using different terminology. So up here we said in this reaction, this E2 reaction is stereospecific because we got one product. This E2 reaction is stereoselective. So first one was specific, second one selective. A stereoselective reaction is a reaction where a mixture of stereoisomers are formed. In unequal ratios. Whoops. Basically, this is a fancy way of saying we get a major contributor versus a minor contributor. We don't just get one product out, we get two products. So we have to be careful with the terminology we use. The way I always remember the difference between stereospecific and stereoselective is, remember, the term specific means you only want one thing, right? Selective means you prefer one thing, but you'd be willing to take the other. So try to keep those two terms clear in your head, because you'll see them pop up in the Klein textbook fairly regularly. All right, we've got one other tricky problem we have to work on. So let's do another E2 reaction. So example number 3. I'm going to draw this out. We've got, okay. This one I'm going to put a CH3 group there, CH3 group there. We've got a hydrogen, and we've got a hydrogen there. All right, I want you guys to help me predict what product we would get from this reaction, or what products we might get from this reaction. So I'll give you guys a minute to work on this next example. And check with your neighbors too. I'll give you a good hint. There's not just one product. See if you can identify all of the potential products. What's the first thing we need to spot when we're doing an E2 elimination? Yeah, we have to identify anticoplanar beta protons. So let's first identify our beta protons. All right, we've got a set of pretty obvious beta protons, right? Here and here. Is that it?
No.
No, we have beta protons up here too, right? So if we look at this, we've got a bunch of beta protons we can select. So let me actually draw these as black bonds. So knowing that, what products might we get out of this?
We probably will pick the hydrogen on the top.
All right, let's pick one of the bottom ones.
It's not.
Okay, so you want to make it anticoplanar?
Yeah. Twist it.
Okay, let's do that. So let's convert this so that it's anticoplanar. So now we've got a hydrogen up, we've got our methyl group down, we've got a hydrogen here, we've got a methyl group here, we've got a methyl group there. Okay, let's do this. Got our base that's negative. It's going to grab our anticoplanar beta proton, clamp down, kick off our bromine. When we do this, our back carbon has two methyl groups coming off of it. Our front carbon has a methyl group and a hydrogen. Fair enough? Do we agree on that product? Are we going to get cis versus trans mixture? No, because we can't really distinguish between cis and trans in this system. We're only going to get one product here. Even if we grab the other proton off of that beta carbon, it would give you the same product for this reaction, right? All right, but now let's redraw this. And I'm going to pick just one of these beta protons over here, and I'm going to have this react with our base. So if our base comes, grabs one of these beta protons, let me actually try to make it look anticoplanar. This will clamp down, kick off our bromine, and what will our product look like? Well, our double bond is now sticking straight up. And then we've got this product here. Let's try to name these. Let's name the top one. So again, we want a number going from our longest carbon chain containing our double bond. So this would be 2-methyl to butene. So we get 2-methyl 2-butene. Or if we did this one, we could say, all right, this could be 1, 2, 3, 4. We could say this could be 2-methyl 1-butene.
Why is the top one not done?
Because you see how the 4 position is a part of our parent
Oh,
chain?
yeah.
Yeah. And we don't really have to account for the hydrogens, they're assumed. Yep.
Can you explain the 2 and the 1? So the 2-methyl 2-butene.
Yeah, so on the bottom one, the methyl group's coming off the 2 position, so that accounts for the 2-methyl. And the top one, the methyl group's also coming off of the 2 position.
I meant the 2-butene.
Yeah, and then for 2-butene, the double bond starts at carbon 2, versus this one, the double bond starts at carbon 1. So we do want to distinguish where the double bond starts by indicating that before the butene.
It goes from 1 to 2.
Exactly.
Okay.
Yep.
So for the second one, the base attached the proton because it's is the proton anticoplanar to Br? Right?
Yes, exactly. So we've got 2 different types of protons that are anticoplanar. All right, what's the relationship between these 2 compounds, between 2-methyl 2-butene and 2-methyl 1-butene? Constitutional isomers. Here we go. So we've got constitutional isomers. So in this case, we're going to get a mixture of products. both products, when we compare them, are going to be constitutional isomers. If we look back up to these examples, what's the relationship between our cis and our trans product? They're stereoisomers. More specifically, are they enantiomers or diastereomers? Diastereomers. So we can label this as diastereomers. Diastereomers are a type of stereoisomer. Versus constitutional isomers, which are not stereoisomers. All right, so when we look at these reactions where we get a mixture of constitutional isomers, we refer to them differently. We say this E2 reaction is regioselective. And regioselective means instead of getting a mixture of stereoisomers, we get a mixture of constitutional isomers.
Are they 50-50?
No, we're going to cover that next. So get a mixture of constitutional isomers in unequal ratios. Do you have a question, Sarah?
How do you know they're going to be equal ratios?
Let's talk about that. So let's take a step back and just intuitively say, all right, which one looks most stable? The top one or the bottom one? Top one. I heard most people say the top one. Why is the top one more stable as a product? It's tri-substituted, right? We've got 3 different methyl groups coming off of the double bond, where if we look at the bottom one, we only have 2 different alkyl groups. We're looking at tri-substituted versus di-substituted. I told you guys earlier this week, the higher the substitution, the more stable it's going to get. That's one half of the story. Let's think about if you're a base and you're trying to grab a proton, which set of protons are more accessible? The protons coming off of the methyl groups on the top, or the protons coming off of the ethyl group? Let's think about this. Imagine you're a big, bulky base, and you're trying to come in here. Let me even mark this up. This carbon is secondary. Whoop. Which means it's less accessible. And if we look at this carbon over here, these protons are coming off of what sort of carbon? Primary. Which means these are more accessible. And this is where the trickiness comes in. Imagine I'm a really giant base. I take up a ton of room. Which proton am I going to go after? The protons coming off of the secondary carbon or the primary? Primary. They're a lot easier to pluck off. If I'm a big bulky base, I'm going to have a lot harder time approaching a secondary carbon than I am a primary carbon.
But what about those hydrogen brands?
Yeah, but let's say I'm a really, really small base. Do I really care which proton I go after? No. So this is, again, going back to reaction coordinate diagrams. You want me to scroll up again? So in this case, we have to look at 2 different things. We have to look at the size of the base and the stability of our product.
But what about bulkiness of the base? Because, I mean, if the base is bulky, it's the one that has a hydrogen branch kind of like, it's bulky as well, isn't it?
What do you mean?
We got 2 bulky things.
Yeah, let's go back to that really quick, but let's draw this energy coordinate diagram and I'll try to address it.
Okay.
All right, so we've got this reaction. We said we've got this starting material, and in this case, our starting material for both reactions looked relatively similar. That was our starting material. And in one case, we said we're going to go form a really stable product. So I'm going to put this product down low in energy. And this product looked like that, right? And we said that it's going to have to overcome some sort of activation energy to get to that more stable product. So we've got energy on this axis, reaction down here. And then we said we have a second pathway where we go to a less stable product, and this less stable product looked like this, right? But we said we were pulling protons off of a more accessible proton, or off of a more accessible carbon. So I'm going to actually draw this in right there. So if we look at the more substituted alkene, down on the bottom, is that going to be a thermodynamic product or a kinetic product, or how would we describe it? Thermodynamic. So again, we're going back to this. This would be our thermodynamic product. Which is code for most stable product. And then if we look at this one, this is going to be our kinetic product. It's the product that has the lowest activation energy. So if you look at the blue activation energy, we're only going up that hill. We don't have to climb that big black hill. But if we're looking at the thermodynamic product, we're not looking at the hill we're overcoming. We're instead looking at the delta G value.
Could there be a situation where you had both a higher activation energy and a less stable final product?
Yes. In that case, your thermodynamic product would also be your kinetic product. Essentially, your thermodynamic product saying all we're concerned with is the difference in stability. And with our kinetic product, all we're concerned with is the activation energy, not the difference in delta G. All right, so if we're looking at these reactions, they actually got named after a pair of chemists. Oh, let me slide this over.
Do I have to draw them?
Yeah, you have to draw these chemists, and I'm going to grade you on the shading. It better be good. I want perspective. This is Alexander Zaitsev, and this is, I think, Wilhelm Hofmann.
Are they German?
Yes. Almost all of the early organic chemists were German. The thing that kind of threw them out of the world power for chemistry was World War II. They didn't fare that very well. But prior to World War II, that's where all of the important chemistry was happening in the world for the most part, in Germany and in the UK. So these were the two chemists that noticed this discrepancy. Alexander Zaitsev was the one who noticed that typically, in his experience, he was forming the more substituted alkene. And Hofmann said, well, in my reactions, I'm actually getting the less substituted alkene. So these products got named after them. The one on the left is the more substituted alkene. And this one described the less substituted alkene. So let's go back up to our products and let's try to name these. If we look at the top one, the 2-methyl-2-butene, would that be our Hofmann product or our Zaitsev product? Zaitsev. So we call this our Zaitsev product. And the 2-methyl-1-butene would be our Hofmann product because it's less substituted. So oftentimes chemists, instead of writing out the full name, they'll just say, oh, this E2 reaction will give you the Hofmann product, and they assume that the organic chemist looking at the paper knows what they're talking about. Yep?
How come the Zaitsev product is a secondary?
So you see how the Zaitsev product, in this case, is a tri-substituted alkene? So that means it's more substituted than our Hofmann product, which is a di-substituted alkene.
But you said the Hoffman was primary and the other one was secondary at some point?
So what I was saying was Alexander Zaitsev said that you'll get the more substituted alkene under his reaction conditions. And Wilhelm Hofmann said you'll get the less substituted alkene. So in this case, we're comparing a secondary one to a primary one. The secondary is more substituted than the primary.
Yeah, how do you know if it's secondary or primary?
We're looking at our substitution pattern. So if you look at your double bond, ask yourself how many non-carbon or how many non-hydrogen substituents are coming off. Again, if we go back and we look at this one, we've got a substituent coming off right here, here, and here, so that's tri. Versus over here, we have a substituent here and here, so that's only di substituted.
Okay, but right there on the left part, it's blue, it says primary and it's more accessible.
I'm just referring to the carbon where the beta protons are coming off of. So when we're distinguishing between our Zaitsev product and Hofmann product, we're just comparing the alkenes that are formed, not the starting material. Yep.
But I'm still confused how you can tell which one's more favorable depending on like the temperature.
Yeah, so let's go through and describe some of the early experiments that were done with this. So experiments. So they actually did this reaction. And this one we've got bromine coming off. And we're going to pick some generic base. And we're going to ask ourselves, are we getting this product? Or are we getting this one? And we said this one's our Zaitsev. This one's our Hofmann. This one we said is more substituted. This one's less substituted. All right, and I'm going to give you guys some bases. No? And I want a percent, Zaitsev and percent Hofmann. All right, we're typically going to get a mixture, but let's say I'm using a small base. So ethoxide, it's pretty small. Is it going to prefer either set of protons coming off of the beta position, or does it really not care? Doesn't care. It's small enough to attack either of them. So in that case, is it going to favor formation of the Zaitsev product or Hofmann product?
50-50.
It's going to favor the Zaitsev product. Small bases tend to form the more thermodynamic alkene. So in this case, they ran this reaction, and that's exactly what they got. They said small bases give majority Zaitsev products at a 71%, and then the Hofmann is still observed in a 29%. What if we used methoxide instead of ethoxide? Do you think that would increase the Zaitsev product or decrease it? Increase it. So we can play these size games with this. And let's choose a new base. So let's use terp-butoxide. In this case, it's pretty big, right? It's got 3 different methyl groups coming off of the base. That means it's going to have a harder time going after secondary carbons or even tertiary carbons. So is this going to favor our Zaitsev product or our Hofmann product? Hofmann, exactly. So in this case, we get 28% and we get 72%. And then last but not least, we get the super big base. Are we going to get mostly Hofmann or mostly Zaitsev? Mostly Hofmann, exactly. So we only get 8% of our Zaitsev product, and we get 92% of our Hofmann product. Yep.
How did you get the percentage for your bases? If you're not percentage, how were you able to have
So this was experimentally determined. But what I was trying to get you guys to do is just to intuitively predict with a large base, are we going to get the Hofmann or Zaitsev? Large bases favor the Hofmann product. Small bases favor the Zaitsev product. Sometimes it's not super clear. Normally I'll give you a super bulky base or a super small base. That way you can easily predict which one will be major or minor. Yeah. So for example, if I gave you an isopropyl group instead of a tert-butyl group, that's kind of in the middle. It wouldn't be super clear. Yep.
So the reason Hofmann always got a smaller one because he was using bigger bases?
Yeah, and he was doing a bunch of different reactions that we're going to talk about later in the year, but he was describing the kinetic product, the one that's more accessible, it has the lower activation energy, where Zaitsev was describing the thermodynamic product. It wasn't that either of them was right or wrong, it's that they were describing two different types of reactions. So let's even make a note. Zaitsev is favored by small bases. This one is favored by bulky bases. All right, I think that's where we're going to end today. Tomorrow, we're going to start going into E1 reactions. And the problem of the day that I gave you is an E1 reaction. And I will give you a hint. It involves more than one rearrangement. So just like with SN1, you observe rearrangements with E1 reactions. So be aware of the potential for that sort of reactivity.